The stepper killer is dead. Long live the stepper killer.
Welcome back to Cloud 42. I'm James. A couple of years ago, I did a series of videos looking at different stepper and servo motor options for my lathe electronic lead screw project. The most expensive option I looked at was a ClearPath servo that they affectionately call the stepper killer, but I also tested a $100 Chinese import servo that I playfully referred to as the stepper killer, and that's ultimately what I put on my lathe. It has served me well for almost 2 years, but now it's dead. Let's determine the cause of death and see if we can reanimate it.
This is my Grizzly Geo 602 lathe, and I have my electronic lead screw installed on it. Let me power it up here, and as this is initializing, I will grab a Sharpie and refresh these blue marks that I have on the spindle pulley and on the lead screw pulley, just so you can see better what's happening here. If you're not familiar with the electronic lead screw, the way it works is I have an encoder attached to the spindle that senses the motion of the spindle, and then a servo motor to drive the lead screw. And as I turn the spindle here, you can see I have it set to 5/1000ths of an inch of feed. The lead screw should be turning, and it is not turning. You can see I do have the RPM registering, so the encoder is working. And in fact, if I spin the motor up, you can see the RPM readout. So I know the input side of the lead screw is working, but the output is not. That servo should be turning the lead screw, and the lead screw motor should be locked up. Doesn't matter how I change the settings here, it is definitely not working, so we need to take a look at the motor and see if we can figure out what's going on. The servo is tucked in on the back of the lathe, so we are going to go handheld. Hang on to your lunch. And there's the servo above the spindle motor underneath the electronics enclosure, and there is no power light. It's on, but the power light is not on. So let's bring in a multimeter and see if it's getting power. This is tight quarters. There's not really room in here for you and my head and the meter, but it should be worth it if only for your entertainment. I'd really like to get on these screw terminals without shorting anything out. We don't want this to be bright and loud and short. And there it is, 43.15 volts. This is a 48 volt power supply, but the maximum voltage on this servo is 50 volts. They recommend 36, so I turned it down as far as I could. 43 should be just fine. Since we know the servo is definitely getting power, it's time to dig it out and see if we can figure out what's wrong with it. The servo is mounted to the frame of the lathe here with 4 M6 screws. This is actually mounted on the 3D printed mount I made in a previous video. This is carbon fiber nylon. The very same carbon fiber nylon that everybody told me in the comments wasn't going to work because it was going to creep over time. Yeah, it's still here. We'll get the belt off, get the screws out, and we can pull the servo out and have a look. Unfortunately, I forgot to disconnect the cables, so we'll get the cables disconnected, and then we'll pull the servo out and have a look. Over here on the bench, I've got my Rigol DP832 power supply. On a single channel, this will only go up to 30 volts, but it should be plenty to test this servo. And this will just rule out any possibility that there's something weird about the wiring in the lathe. I've got it set to 30 volts, 1 amp maximum, and we'll switch it on. And the power's on. It looks like we are drawing about 100 milliamps, but there are no lights. So it definitely isn't a power supply problem. You can see we are pulling 98 milliamps though. So that power is going somewhere. If the motor's not actually coming on and the coils aren't energized, there's no resistance to turning this, that means that power is not going into the coils and must be being dissipated in the circuitry. So something's definitely not right. I'll turn this off, get this thing unplugged, and let's take it apart. I'll start by removing the mounting plate just to get it out of the way. If you look closely at this, there is a little bit of a bend to it, so it looks like there was a little bit of creep, but over the several months this was on the lathe, it wasn't enough to cause any issues, so we'll set that aside and use that again. Servo is held together with 6 screws here on the back. It looks like the top 2 are self-tappers into the plastic, and the other 4 are machine screws that thread into the metal frame of the motor. And with those off, we can pull it apart. It's like the back cap has some thermal compound, and there are some thermal conductivity pads here. And there are the 6 transistors to drive the 3-phase motor. So it's a nice little solution to heat sink those parts. And then it looks like the rest of this is held in with 2 more self-tapper screws that are just holding the PC boards in. And with those out, we should be able to pull this out, though that top board is trapped in a groove. It's just held on with a couple of headers, so we'll pop the back board off and then we should be able to get it out. And the label is also trapped in a groove in there, so this looks like a real simple construction. Top board looks like just interfacing for the connectors, and then that plugs onto the other board that has the microprocessor and the motor drivers. And then that board is held to the motor by the 3 motor wires that look like they're just soldered on, and then there's a header connector for the encoder. Everything in here is gooped up with adhesive. That's good. It's not going to come unplugged, but it does make it a little bit hard to separate. But with a little prying, it'll come right off, and that will allow us to flex this board out enough to see what's on it. Now, since I'm old, I need magnification. Normally I would use a jeweler's visor, but I've been experimenting with these. These are dental magnifiers, and these have a 420 millimeter focal distance, so I can sit up straight and still see a magnified view of what I'm doing. Let's take a closer look at these boards and see if we can see anything weird or if we can understand what's going on here. This top board looks like it really is just connectors and interfacing logic. Got the power input here and some big fat traces that come down to these headers where it feeds onto the other board. The LEDs here there's a power LED and a status LED, and those don't look to be connected directly to the power here. They look to be connected to pins that go down to the other board. So I think the power is feeding down along with the other connectors for the serial and the stepper inputs. And then all of the work is being done on that other board. Not sure what this is. That looks like an optocoupler, probably related to the stepper inputs. And then we've got some fuses and looks like a reverse polarity protection diode. Power comes in here. We've got the protection diode across that and then a couple of fuses in series. The positive pin is down. So when I flip this over, that'll be up. Yep, and that goes through the fuses. And we can check some of the things on the board here. Let's check and make sure those fuses are good. And they're good, though if they were blown, we wouldn't see any current draw at all. And if this diode were damaged or shorted, we would see a lot more than 100 milliamps. So in the positive direction, we've got nothing. If you hook the power up backwards, looks like we got a drop of a little under 0.6 of a volt. That sounds about right. I think this is all good. And I don't see any blowholes or any burn spots or smoke damage or anything on this. I think this board looks clean. Let's take a look at the processor board. First place I would expect to see damage would be on the high power components, these transistors, but these look clean. I don't see any cracks or smoke or burns or any damage to those at all. In fact, everything on this board looks clean. We've got a voltage regulator here. This is an AMS 1117 3.3 volt linear regulator. Then here we've got a diode. I'm not sure exactly what purpose that's serving. Then on the other side, we've got the processor. Looks like some drivers, maybe a flash memory. This all looks good. I don't see any damage on this thing. Looks like the power comes in on these pins here on the end. Looks like maybe a current sense resistor that feeds up to the power supply section. Okay, this makes sense. This is a switching buck converter. We've got the coil and the capacitor, and then this is probably the controller chip. So the high voltage is coming in through a set of filter capacitors, going through the buck converter. That steps down the voltage far enough that it can be safely handled by the linear regulator, which will provide a nice clean 3.3 volt rail for the microprocessor. Then the processor's here. This is an STM32, still has the markings on it, which is a little bit unusual for this kind of hardware. And then I suspect these chips down here are drivers for the transistors on the backside. And then we've got the encoder input. That'll just go straight down to the microcontroller. There's a programming header here. There's a chip with the markings lasered off, and this is probably a flash EEPROM for the microcontroller. I don't see anything wrong here. Let's power it up and start by checking the voltages. Actually, before I check any voltages, let's check the electrolytic capacitors. We all know that they are the bane of our existence. I've got my LCR meter here with a tweezer probe, and we'll start with the main input filter capacitors. And we're mostly just concerned about the equivalent series resistance. And this is reading 0.07 of an ohm. That's actually really low. Those are good quality power supply capacitors. At least they're working well. Yeah, those look good. Those two are in parallel, so they should read exactly the same. There's a couple more capacitors here. They look to be related to the low voltage DC supply. And if I can get good contact here, 0.39 ohms, that's actually not too bad, especially for a smaller capacitor. This one's closer to an ohm. I still don't think that's an issue on a small cap on a linear regulator. I think this should still be fine. These things, I know the AMS 1117 functions fine with a 2 ohm ESR cap. Checking the cap on the buck regulator, that's about 1/3 of an ohm. That looks fine too. I don't see anything here in the capacitors that causes me concern. Let's go ahead and get some probes and check some voltages. Since we're going to power this up, I'll go ahead and plug the encoder back in. I don't think it'll matter, but I want to reduce the number of variables here. Let's start by checking the logic voltage for the microcontroller, and that's going to be on this linear regulator. AMS 117 is a 3-terminal device. It's got a ground, output, input. This is not an adjustable version, so that pin on the left should be at ground potential. Go ahead and plug the top board back in just so that we can supply power to it. And then of course I'll grab my old man glasses so I can see what I'm doing. And I'll grab a couple of little mini grabber probes and use those to connect to the pins of the regulator. Connect to the ground pin, and let's start with the output. This should be 3.3 volts if everything is working correctly. Power up the supply, and 1.65 volts. That is not 3.3. So we definitely have a problem here. The regulator is not outputting the 3.3 volts required for the microcontroller. Let's power down, and now let's check the input and see what it's receiving. And it looks like it's receiving less than 3 volts from the buck converter, and that would be why it can't produce 3.3 volts output. Now the question is, why is it only receiving that much? Because if there were just something wrong with it and it wasn't outputting the power, I would not expect to see the heavy current draw that we're seeing. So I suspect something downstream from this regulator is pulling additional current and pulling that voltage down. Let me just do a sanity check by checking the input voltage here. And yeah, that's still 30 volts. So I suspect that the excess current draw is just pulling down the output of the buck converter. And if that theory is correct, it should be turning into heat, and a thermal camera should be able to tell us where that's happening. I just have a little thermal camera that attaches to my phone. It's not great, but it's good enough for this kind of application. And with the board powered up, you can see we've already got a hot spot developing. I've got a little bit of parallax here between the visible outlines and the thermal image, but that hotspot is the 3-terminal linear regulator. So if something is pulling excess current through it, this is consistent with that. It is getting hot. Nothing else on this side really seems to be hot. Let's flip it over on the other side and see if there's anything to see there. And yes, there definitely is. And unfortunately, that component that's showing 73, 74 degrees is the microcontroller. That's the STM32. So I don't think this is something we're going to be able to fix. The microcontroller itself should not be able to draw enough current to generate those kinds of temperatures. If we had something else on the board shorted, an individual GPIO should not be able to pull enough current to generate that kind of temperature. You can see if I pull back so the cameras align better, it's definitely the STM32 that's dead there. Must be some kind of internal failure, some kind of internal short. Even if we wanted to replace it, we can't extract the firmware from the existing chips, so I think this servo is done. It's really too bad. I was hoping to be able to fix this. Now, this servo came from Stepper Online, and just in case there is any confusion though, they don't actually manufacture it. It was made by Leadshine. There are a whole bunch of different servos that look very similar to this under different brands, but I would be willing to bet Leadshine makes them all. So what now? I can't live without the electronic lead screw. I thought seriously about getting a ClearPath servo so I'd know I had something that was good quality, but that would require me to reconfigure things. So I'm lazy. I just bought another one. These are $99, and I think the money is worth the risk. The servo has worked really well for me. I don't know if this was just a one-off failure or if it's a class issue, but it's worth 99 bucks to me to take that risk, especially since it's going to save me the time of reconfiguring everything. Let's do a little test here just to make sure that this works. And yep, it powers up, the rotor locks. So yeah, it was definitely the failed servo, which, I mean, we already knew that. To use this though, I do need to program it. It comes by default set to 4,000 steps per revolution, and I need it set to 500. The servo actually came with the programming cable, which was a pleasant surprise. This just has a DB9 serial connector, so we need a USB to serial converter. If you've seen my previous videos on this type of servo, you'll know that the off-the-shelf ones that I bought at my local big box store didn't work, but I got one direct from Stepper Online, and that one seems to work fine. I've got the USB cable connected to my laptop. We'll power on the servo and start up the software that I downloaded from Stepper Online. Now I know that this USB cable connects as COM3, so we'll select that and click search. And it's just scanning through all of the possible driver addresses until it finds it. And it says find drive 63, we'll click connect. There are the version numbers. We'll click the second button here, which is for the parameter manager, and here's the value we're concerned with. Microsteps, we'll change that from 4,000 to 500. Hit enter. Click download to send it to the drive, and then save to make the change permanent. There's the dialog, says it was successful. That should be all we need to do. Now we just need to unplug this and take the servo back over and reinstall it in the lathe. And here's where buying the same servo, i.e. laziness, pays off. Got the same bracket right back on the new motor, and it will just slide right back in whence the old one came. 4 screws hold it in place. And a couple minutes of work, and we will have a servo back in the lathe. Got the belt tension about right. Everything's moving freely. Let's hook up the wires. And we should be ready to test. Just power it on here. And it looks like the servo is energized. And it's turning. That's a win. Let's power it up. That looks good. Change the direction. That looks good too. I think we are ready to make some test cuts. I've got a piece of aluminum round here in the chuck and a polished aluminum insert in the tool holder, and we'll just take a pass here and clean this up. I have the electronic lead screw set to a feed of 5 thou per revolution, and that seems to be working well. I mean, the chip formation is terrible, but the feed's working well. Now let's switch over to a threading tool and try a threading operation. Put a little bit of blue Sharpie on the part here to make it easier to see and easier to check and make sure we're getting the right thread pitch. Got the electronic lead screw set to 12 threads per inch. We'll just touch off, feed in a little, and take a pass. I've got my thread gauge here. We'll grab the 12 thread per inch leaf and looks good. Looks like we've got everything configured properly. We are back in business.
Am I an idiot for buying the same servo that already betrayed me once? Or am I a genius for choosing the cheap and easy option and saving myself some time? I guess we'll all have to read the comments and find out. If you enjoyed this video, give it a thumbs up. Feel free to subscribe and maybe think about supporting the channel over on Patreon. Patrons get access to downloadable files for all of my projects, and I regularly post lens clips for a little peek behind the scenes. Thank you for watching.